Video 5, Chapter 9. In addition to performing the same 3 C's that you did for confidence intervals, you must also state your hypotheses, your null and alternates, and define your parameter of interest, which all that meant was if you were doing a mean level problem, you would need to write that mu equals, and then write in context related to the problem what mu really should represent. So our 3 C's again were our conditions or calculations and writing a conclusion. So now this is kind of where the 4-step process of the book, sometimes in questions would say, perform the 4-step process. This is kind of the 4-step process at this point if you want to think of it that way. This is step 1, here's step 2, here's step 3, and here's step 4. Okay, but I'm still not going to call it the 4-step process. I will just say, we have to state and do our 3 C's for hypothesis testing. Now, conditions. Conditions are pretty much the same thing as they were before for confidence intervals. Your random, is this right? Random, yeah. Our random condition, we have to make sure that it's random. If it doesn't say it's random, then we will say random not known to be random, but we will assume that it is, proceed with caution. If they, mention that it's from a call-in poll or some sort of sampling method that will produce a high level of bias, then we're just going to stop. Okay, it's not worth calculating and doing any type of statistical work with. Okay, but you need to mention that the sampling method is not random at all and will produce results that aren't favorable. We still have the independent check or the 10% condition. You still need to check if the population's at least 10 times your sample size. And you do need to state specifically in context, what is your population? It's all what? And typically, whenever you look in the problem and it tells you how big the sample size is, when it tells you what the n value is, usually right after that, whatever they sampled, then that's what you also need to say in terms of all for your population. And if that is okay, then we may calculate the standard error, and the standard error was either our sigma sub x bar or sigma sub p hat, which had its own, each of these had its own formula to work with. If that does not work out, technically we could use the finite population correction, but we won't in this beginning level stats course, but you certainly will and could in future math or stats classes. Now the one thing that's going to look a little bit differently is the normal condition. And the first thing to note here with the normal condition is the central limit theorem does not work with proportion problems. So it doesn't matter if you have a sample size that's 1,000. You can't use the central limit theorem here. Now you're still going to use the n times p and n times 1 minus p. But what looks a little different right now is that it's not p or p hat. We kind of call it p sub naught. Okay, where p sub naught is your hypothesized value for p. So for example, if you had your null hypothesis and maybe we were talking about the 62% claim from CADA about the proportion of students who drink alcohol. So we're going to test the claim, is it 62%? Well, this 62%, that is that p sub naught number. That's the number you're going to put in to both of these spots. Okay, so it's whatever you're testing, that will be what you plug in for the n times p and n times 1 minus p, not what you get from your sample. That is your p hat. We're not going to use that. So that's really just the one main difference here with the conditions. Calculations. In video 2, we discussed the concept of a p-value, which was our total evidence against the defendant, if we were talking about the jury case here, in comparison to the significance level. And the significance level was our tipping point from saying that someone was innocent to saying they were guilty. Okay. Another way we kind of described it in class was the significance level is that dividing line between calling something a rare occurrence versus it's not really that much of a rare occurrence. And if it is a rare occurrence, that means we have a very small p-value, smaller than our alpha level, and we would reject the null hypothesis. So now we need to talk about how to exactly calculate that p-value. Because before I just gave it to you, and I said, let's pretend that these people in these problems really correctly calculated a p-value. Now let's talk about how to use that p-value. All right, so here is the general formula, and this is in your formula sheet. Okay, this doesn't give you exactly everything you need here, but we are going to be calculating a standardized test statistic. Okay, and if you remember from the confidence interval chapter, our standardized test statistics were either z or t. And z's we're going to use in proportion problems, and t's we're going to use in mean problems. So since we are in this section, in section 9.2 of the book, we're going to be focusing on proportions. So for now, we are going to be focusing on calling this a z. We're going to be solving for a z-score. We're going to figure out, how many standard deviations away is the result from our sample away from our hypothesized value. So our statistic, and we'll get more into the specifics of this formula, but the statistic is going to come from our sample. The parameter is going to come from our population. This is where our claim is going to come from. And then for now, I will just give you this value, standard deviation of the statistic. In the next video, we'll talk about exactly a formula that we could turn all of this into. So the test statistic, as I mentioned before, is really just a z-score for right now. If we're going to do a mean level problem, then it's really going to be a t-score. And so our z-score just says how far away our actual sample value is from our hypothesized population value. If it's far enough away, then our null hypothesis is more than likely wrong. It's not definitely going to be wrong, but more than likely, because we mentioned in a previous video about type 1 and type 2 errors. Now, when we did confidence intervals, I told you not to worry about the negative sign that you would get with your z-score when you used inverse norm, or a t-score when you get inverse t. But we do need to keep whatever sign that we get in our calculator now, because we're no longer going to be adding and subtracting that z-score or that t-score like we did with confidence intervals. So the sign that you get in your calculator for your z-score using inverse norm, we're going to keep that number. And we're not actually going to use inverse norm and inverse t in this chapter. But if you remember from the confidence interval chapter, when we used inverse norm, maybe we got a negative z-score. And at that point, we just said, we're just going to chop off the negative. Don't worry about it. Now we do. If it's negative, if we come up with a value and it's negative, we want to keep it negative. If we get a positive, it's going to stay positive. So you'll see what I mean as we get through more and more of these videos here. Now, a z-score is from a standard normal curve, which means it just has a mean of 0 and a standard deviation of 1. So we don't have to worry about putting in 0 and 1 into our calculator, which will be more revealed here when we get to this part. The p-value is the area under the curve as extreme or more extreme than this z-score, this test statistic. Okay, so for example, this might be, oh, that's not really a good example there, but we might be finding the area under the curve, like maybe here's our z-score, and this will be our p-value. Okay, and the smaller this number is, the farther it is away from our hypothesized value, which is right here in the middle, and we would conclude that we have a bad null hypothesis, and we would go in favor of the alternate hypothesis. Now, remember how to find the area under the curve with lower and upper bounds. So for example, if we looked at this example, if I wanted to figure out what the area of this green shaded region is here, how could we find the area of this? Well, here's where, in the confidence interval chapter, we used inverse norm. In this current chapter, we're going to use kind of the opposite of inverse norm. So we're going to go back to using Normalcdf. Now the good thing is when we use Normalcdf, remember we had our lower bound, our upper bound, and then we had to put in mean and standard deviation. But we're always going to be working with a standard normal curve that always has a mean of 0 and a standard deviation of 1. Now those are the default values for mean and standard deviation for Normalcdf. So really we can just stop after the upper bound. We don't have to put in 0 and 1 because by default it will put them there for us. So really we're just going to be putting in the lower bound and the upper bound values for normal CDF. And whatever answer that we get from that, that is our p-value, okay? And that's what we're going to be comparing against our alpha value. Now, we will need to draw a normal curve, but then we need to talk about, well, which way are we going to shade? Are we going to shade to the left, to the right? Which way are we going to go? Well, the shading depends on the sign used in the alternate hypothesis. If our alternate hypothesis uses a less than sign, so for example, this picture down here, okay, and the blank is just whatever, whatever kind of problem we're working on there. So if we use a less than sign, typically we should have a negative z-score. It's not always going to be the case, but that should be what we should end up with there. And if we're talking about less than, then we're going to shade to the left, because that would be less than our z-score. And so that's going to be our p-value whenever we use normal CDF. So our lower bound would be negative infinity, and our upper bound would be whatever that z-score is. Okay? If we use a greater than sign in our alternate hypothesis, like this, for example, then chances are, this isn't always going to be the case, but chances are our z-score is going to be positive. It's going to be on the right side. And so we're going to shade to the right, the greater than that z-score. So now our z-score is the lower bound, and positive infinity is now our upper bound. And again, the area that we find there, that's our p-value. And if our alternate hypothesis uses a not equal to sign, then we're going to shade on both sides. This is where it's going to get a little bit different. Let's say, for instance, you get a positive z-score. Well, you can certainly put the positive z-score down here, but we're also going to mark the negative version of it. Because when we say we don't know whether it's greater than or less than with a not equal to sign, we have to consider both cases, that maybe it is greater than or maybe it is less than. And then we're going to shade to the outside of those two. We're going to shade less than this negative version and greater than the positive version. So here's where else it's going to change slightly. We're technically going to have two areas we're going to be finding. Now, the good thing about this is we only really need to find the area of one of these two ends, because the nice thing about a normal distribution is that it's symmetric. So this right end and this left end will be the same exact value. So all we'll really need to do in the end is double our p-value. So again, the only time we're going to double a p-value is when our alternate hypothesis uses a not equal to sign. We don't double when we use greater than or less than, because we're only talking about one direction. And this is called a one-sided test. A not equal to sign is called a two-sided test, because we don't know which side we're really going to be on. So we might be on, the less than side or the greater than side. And last but not least, our conclusion. If our p-value that we calculate using normal CDF, if it is too low, if it's less than our alpha value, then we're going to reject the null hypothesis in favor of the alternate. So again, if the p-value too low, the hoe gotta go. So here's my, he's trying to be the ladies' man, but he totally can't be the ladies' man. So he's saying, yo, skank, you gotta get going. Your p-value too low. And she's like, okay. Oh, wait, let's unattach her. There we go. And she's like, all right, I guess I'll just leave through the imaginary door here. And then, oh, she's gone. And he's like, yay, she's gone. Yay, she's gone. I can finally make some more money. So the example we're going to look at here. You want to test the notion of home court advantage, that the home team wins more than half of all games. Out of 30 NBA games between January 3rd and 7th, 1992, 18 were won by the home team. We will assume all conditions have been met. The standard deviation of the statistic is 0.09129, and we will calculate this value in the next video, so don't worry about how I got this number. First, we're going to state the null and alternate hypotheses. We will then calculate our test statistics and p-value, and then what would we conclude at the 5% significance level? Okay, so our hypotheses here, our null hypothesis and our alternate hypothesis. Now, it doesn't really give us a percent up here to work with, but if we notice, it says the home team wins more than half of all games. So we want to see, is home court advantage a real thing? So our null hypothesis is that there really is no difference. That winning at home and winning away, you still have a 50-50 chance. But if there is such thing as a home court advantage, then we would expect to win more than 50% of our games. So this is what we want to try to show. We want to try to have enough evidence against that it's really 50-50 in favor of that it's really more than 50 for a home court advantage. So now we've stated our null and alternate hypotheses, and we'll go ahead and define our parameter here. P is the proportion of, we'll be more specific here, of home games won, do we need to specify NBA? What do you think? Sure, why not? By NBA teams. Okay, so now calculating our test statistic. Before I said the test statistic, let's move some stuff up here. Do I have it on the next page? Hey, I do, what do you know? Is this right? Yeah. So our statistic, here we go. This is where I wanted to be at. Our standardized test statistic is the statistic minus the parameter divided by the standard deviation of the statistic. The statistic is what we got from our sample, which was that 18 out of 30 games were won by the home team. So that is 60%. Okay, and we're going to put it up against our parameter, which is our hypothesized value of 50%. Okay, so right now we're 10% above our hypothesized value. But is 10% enough to say that this 50% we should throw out the window and we should reject the null hypothesis? Well, here's our standard deviation, which is a little bit less than 10%. So you can kind of think about if we're 10% away and we have a standard deviation of 9%, we're a little bit over one standard deviation away from the mean, where the mean is our 50% here. So if I want to apply this formula, and again, for proportion level problems, our test statistic will be z, just as it was in confidence interval problems. So my statistic is my 60%, this is what I got from my sample, minus my parameter, which came from my null hypothesis, my 50%, divided by the standard deviation of the statistic, which I gave you for now, which later you will calculate. And so I get a z-score of 1.095. And again, this z-score just tells me how many standard deviations above the mean that I'm really located. Okay? Now, you do have to do this as part of your calculations. Okay? You don't have to write this formula, but you definitely, well, you'll have a specific formula that you will write that you will learn about in the next chapter. But for now, just stick with this. And now, this is our test statistic. We now need to know a p-value. So here's the next step in that process. And this should look fairly familiar because we've done this before. First, we're going to write our probability statement. We need to find the probability that we find z-scores that are, and I'm going to put an or equal to sign here, greater than or equal to 1.095. Because we mentioned before, our p-value is any value that is as extreme as or more extreme than. Well, as extreme as is our equal to sign here, or more extreme than is our greater than sign in this case, since we're dealing with a positive z-score. So I'm going to use normal CDF, and again, if we're going to use normal CDF, you have to have a picture drawn. 0 is always going to be our center value because this is a standard normal curve. So I found where approximately a little over 1 standard deviation is, and I shaded greater than it. And so this is going to be my p-value here, which is, once I put in my lower bound of 1.095 to infinity, is 13.68%. Okay, so if I'm to interpret this p-value here, I would say, assuming that really home teams have a 50% chance of winning their game, then I would expect seeing a result of 60% based on a sample of 30 in about 13.68% of the time naturally. Now, is 13.68% low enough that we would reject the null hypothesis? And you can see down here by my conclusion, no. It's not less than our 5% significance level, our 0.05 alpha level. So we would fail to reject the null hypothesis. So really, in the end, we do not have enough evidence to conclude that there really is such thing as a uh, home field advantage for NBA teams. Now here is some extra practice. This is in the book. Again, you can pause the video at this point and kind of look this over. So go ahead and pause. And then here's the solution to this. Hopefully you can read all this. Some of the stuff may get a little tricky to look at. You will end up with a very teeny tiny p-value down here. So that's why you hardly see anything shaded. So if you want to look at this, go ahead and pause. And again, well, they may talk about using table A, which is using, the tables in the back of your formula sheet, which we're not really going to do. You can if you want to, but we're going to be using the calculator. So if we use the calculator, you're going to have to draw your normal curve. And this is the problem I want you to bring to class, okay? And this is where it's going to start maybe getting a little bit more in depth. So you definitely may want to try some of these problems. All right, so, jumping ahead here. Oh, that's awesome. There it is. Okay. So go ahead and pause the video, read over this, write this out, and bring it to class tomorrow. We'll see you then.